So guys, in this lecture, we are going to look at tonicity and calculation of tonicity for intravenous preparations specifically. Now, when we talk about tonicity, the best place for us to start this lecture is to actually talk about the different types of solutions we have. Of course, I believe most of us that have read the material know that we have three types of solution. We have the hypertonic solution, right? Then we have the hypotonic solution, and then we have the isotonic solution. Now, the hypertonic solution are those solutions that have a tonicity that is higher, or the concentration is higher than those of body fluid. Is that okay? Now, most preparations are not usually hypertonic, but in edematous patients where you need to actually withdraw some water from such patients, from such patient's tissue, what you actually do is to give those hypertonic solutions. I know these things now. Then the next one is hypotonic. Hypotonic are the ones that are having lower concentration as compared to the concentration of body fluid. Is that okay? And then isotonic solution are the ones that have equal concentration as the concentration of the body fluid. Is that okay? So that is the general idea on tonicity. Now, most intravenous infusions are usually at most very close to what? Being isotonic, or most times they are isotonic solution. Now, isotonic solutions, when you actually give this hypertonic, hypotonic, isotonic solution to a particular patient, maybe to through or via IV injection, now different things can happen. If you give hypertonic solution, and this is, let's say, the normal patient's cell, right? What will happen if you give hypertonic solution? The cell will what? Will shrink. Are you getting it now? And it will deform. So instead of you having it in the normal form, the shape which will actually change. So this one is when you give hypertonic solution. Now, how about a situation where you give hypotonic solution? What will happen? The something go swallow water, abi? Then at the end of the day, what will happen? It will swell. Is that okay? Now, the movement of fluid through a semi-permeable membrane. For instance, in this case of hypotonic solution, where do you think the fluid will move from? It will actually move from the body fluid. Are you getting it? Or from the body fluid into the what? Into the cell. Because when you are giving hypertonic solution, what will happen? The cells will be less, the tonicity, the concentration of the cells will be less than that outside. So what will happen is that water, fluid will move into the cell and then it will swell. I will say the movement of fluid or water through a semi-permeable membrane is called osmosis, right? Something that we've learned before. And the pressure that is actually regulating this process is called the what? The osmotic pressure. Now, my dear students, osmotic pressure is a colligative property. Osmotic pressure is a what? A colligative property. Now, what are other colligative properties that we know? We talk about the freezing point depression, boiling point elevation, etc. Are you getting it now? So when you want to actually measure tonicity, you can use any of these colligative property to measure it. You can use the boiling point elevation, you can use the freezing point depression, you can even use the osmotic pressure, but since osmotic pressure, you cannot easily calculate it, most times they go with the what? The freezing point depression. Because once you know that two substances have the same freezing point depression, it means that those two substances are what? Isotonic. Are you getting it now? So what we actually tend to do in this particular lecture is to prepare isotonic solutions, especially the ones that involve sodium chloride. We are going to be using sodium chloride enough in this lecture. So our aim is to prepare isotonic solution. Is that okay? That's the aim of this lecture. Paying close attention to the freezing point depression. Now, the calculations is what actually matters. I I just needed to give a background of what we are actually doing in order for us to really understand it. All right, so is that okay? So let's use this calculate these questions here. What I will just be doing is to just be answering different questions using the knowledge of what we are going to be getting. Now I say when 1 gram molecular weight of any electrolyte. Now what are electrolytes? Electrolytes are substances that dissociate in water to form what? Ions. That positive ions or what? Negative ions. When 1 gram molecular weight of any electrolyte is dissolved in 1000 gram of water, the freezing point of the solution is about 1.860 degrees Celsius below the freezing point of pure water. So it means that when you actually put in 1 gram molecular weight of any electrolyte into 1000 gram of water, there is a freezing point depression of freezing point. Let me just put freezing point depression, right? What was the freezing point depression would be said to be? What? Minus 1.86 degrees Celsius. I use minus to tell you that it's actually a depression in the freezing point. So whenever you actually dissolve 1 gram of any electrolyte in 1000 gram of water, the freezing point you are actually expecting will be what? Minus 1.86 degrees Celsius. Now, the freezing point depression of lacrimal fluid. Lacrimal fluid is what? The fluid from what? Tears. Are you getting it? Blood, body fluid is about minus 1.52. Or sorry, minus 0.52, not 1.52, minus 0.52. Is that okay? So this is the freezing point depression of body fluids. Is that okay? The freezing point depression of body fluid is about minus 0.52. Now, it means any electrolyte you must inject into the body, right? Anything you must inject into the body must have a freezing point depression equivalent to what? 0.52. Do you understand? Now, what we tend to do now, we want to know how much of the boric acid we are going to measure and dissolve that will give us this minus 0.52. Is that okay? That is what we actually need to know. So this one now is like the standard. Any solution you are preparing must have this tonicity of what? 0.52. Do you get it? So we want to know how much of any electrolyte we are going to dissolve that will give us this 0.52. But we know that 1 gram molecular weight of any electrolyte, when you dissolve it in 1000 gram of water, gave freezing point depression of 1.86. So we can come here. Now, 1 gram molecular weight is still the same thing as the molar mass. That is the meaning. 1 gram molecular weight is still the same thing as the word, the molar mass. So, if they say calculate the weight of boric acid that will produce isotonicity with lacrimal fluid, what they're asking you is calculate the weight of boric acid that will give you a freezing point depression of 0.52, because we know that once it has a freezing point depression of 0.52, it is now isotonic with the body fluid. Do you understand? So our intent now is to calculate the weight of boric acid, but I already said that 1 gram molecular weight of any electrolyte is equivalent to what? The molecular mass of that electrolyte. Now, molecular mass of boric acid is about what? The molecular mass was given as 61.8 gram. Is that okay? So it means 61.8 gram dissolved in 100 gram of water gave freezing point of what? 1.86, abi? Now, so we can say 61.8 gram gave what? 1.86 degree Celsius. True or false? Therefore, S gram is supposed to give what? 0.52. Is that okay? So that at the end of the day, when you cross multiply this now, what do you think is going to give to us? Maybe if you press your calculator. So this will be 1.86 times x is equals to 61 times 0.52. So divide both sides by 1.86. 1.86. Now, when you cancel this, your x would be equals to, what did you get as your answer? 17.05. Okay, this is supposed to be 61.8. So if you do that, you're supposed to get 17.28. Right? 61.8 times 0.52 divide by 1.86. 17 point what? 17.28. All right? So that is that. So this one gave us 17.28. So that is the amount of what? Boric acid. You need to dissolve in what? 1000 gram. Remember that it is in 1000 gram they dissolve this 61.8 inside. I gave this. So you need to dissolve 17.28 in 1000 gram to give a tonicity of what? 0.52 to make it isotonic. But most time, so you can say this is gram per what? Per 1000 gram of water. Abi? Now, but most time, they usually give it in a percentage. Do you understand? So you might decide to say, okay, if 17.28 is equals to 1000 gram, 1000 gram of water is still the same thing as what? 1000 mil of water, right? Because the density of water is what? Is 1 gram per mil. So 1000 gram of water is equals to 1000 mil. So if 17.28 is to 1000 mil, therefore, now it is usually expressed in percentage. Percentage is how many mil? 100 is in 100 mils. So you say this is equals to what? 100 mil. Is that okay? Now these things can actually cancel out each other. At the end of the day, say therefore x is equals to 100 mil. When this multiply this and then you divide it by this, it's going to give us, let me just, there is a way you can calculate it. You can cross multiply, but I can decide to cancel 100, 100, 20 from here. This 10, we cancel this, we divide this 17.28, right? It's going to give me 1.72 percentage. Are you getting it? Weight by what? Volume. So this is the amount of boric acid that is isotonic with body fluid. 1.728 percentage by weight. Is that okay? So that is what we are going to use to solve every other question. Now this is for boric acid. Now boric acid is a non-electrolyte, so it does not dissolve in water. It does not dissociate in water rather. Is that okay? So how about substances that dissociate? For instance, sodium chloride dissociates in water. And colligative property actually deals with the amount present and not the concentration most time. It talks about how many are there. Are you getting it now? So, for instance, sodium chloride is a weak electrolyte that dissociates about 80% in solution. What mass of sodium chloride will produce the same tonicity as body fluid? Now, to actually calculate this, what you need to do is, there's a formula for this. All right? So, to calculate the gram of solute, let's just go straight. To calculate the gram of solute per 1000 gram, you know the one we just calculated just now is still the same thing. The gram of solute that is present in what? 1000 gram is of water is equal to, the formula is 0.52, which is the tonicity of body fluid, times the molecular weight of the compound divided by 1.86, right? Times what? The dissociation factor. Is that okay? Now, the question now is, what is the dissociation factor? I will just indicate it with I. I is the dissociation factor. Is that okay? The question now is, what is the dissociation factor? That is one thing you need to understand what it is. Now, when we talk about dissociation factor, we are talking about the take the formula. Dissociation factor is equals to the number of particles, right, after dissociation, this formula is not in the material, divided by the number of particles before dissociation. Are you getting it now? So this is the formula for dissociation constant. Number of particles after dissociation divided by the number of particles before dissociation. That is what the dissociation constant is all about. Number of particles after dissociation divided by number of particles before dissociation. So let us calculate the dissociation constant for sodium chloride. Now look at it. Say sodium chloride is a weak electrolyte that dissociates about 80% in solution. Right? Now if sodium chloride dissociates about 80% in solution, look at it. 80% in solution. Now let's assume there were 100 particles. So number of particles before dissociation will be what? 100. Abi? Is an assumption because we want to calculate dissociation constant. Let's assume that the number of particles before dissociation is 100. If the number of particles before dissociation is 100, now what do you think the number of particles after dissociation will be? If 80% dissociate in solution. Now, you agree with me that when sodium chloride dissociates, it forms how many ions? Sodium ion and what? Chloride ion. Right? It means that if some fraction of sodium chloride dissociates, it means we are now having how many particles in solution? 3. Are you getting it? Because not all dissociated. Do you understand? If only some dissociated, it means we are not having 3 particles. What are the 3 particles? One is the undissociated one, which is, in this case now, if 80% dissociate, it means undissociated one will be how many? 20. Are you getting it? And then we are going to have what? 2 ions that are dissociated. So the 2 ions that are dissociated will be 80%. So each of them will be what? No, not 40. Each of them will be 80, 80. Do you understand? Because when they dissociate, they form individual ion. Do you understand? So 80 of sodium chloride will form 80 of sodium ion and 80 of what? Chloride ion. It's more like you have 80 of this. When it breaks down, it forms 80 sodium plus what? 80 chloride ion. So the total number after dissociation now will now be how many? You recall that 80% dissociated. So total number will be 80 plus 80 plus 20, which is equals to 80 plus 80 is what? 160. 160 plus 20 is what? Is 180. So number of particles after dissociation will now be how many? 180. Do you understand that? So that was how they were getting those 180 you can see in the material. Now, so our dissociation constant will now be what? A dissociation factor. Number of particles after dissociation is 180. Number of particles before dissociation is what? 100. So 180 divided by 100, what would that give to you? 1.8. So our dissociation factor is what? 1.8. Now, if we substitute that into this equation, dissociation factor is 1.8. So we can erase all this and then try and substitute that into the equation and see what we are going to get. So I is 1.8. So what will be the gram of solute per 100 milligram of solution? Gram of solute per 100 milligram of solution will now be, it will now be 0.52, right? Then times, what is the molecular weight of sodium chloride? 58.5. Because sodium is 23, chlorine is what? 35.5, which is 58.5 divided by 1.86 times, what is the dissociation factor we just calculated? 1.8. Oh yeah, when you calculate this, it's going to give you the correct answer. What did I give to you? Supposed to give you 9.09 gram per. Record that this is per what? 1000 ml of water. Because when you talk about 1000 gram of water, it's saying that's what? 1000 ml. Now, but most times they report it in percentage, like I said. So you can say 9.09 gave us what? 9.09 gram gave us what? 1000 ml. Percentage means 100 ml, abi? So this will be 100 ml will be equals to what? X. At this point in time, we cannot cancel. Told you before, this you can cross multiply and do your calculation. But you can also make it easier, or let's cross multiply and do the normal this thing, because some persons will still get confused here. So when this multiply this is going to give us 9.09 times 100 will be equals to 1000 ml times what? Times x. So divide both side by 1000. Divide both side by 1000. And when you cancel this is going to cancel this. This one here will cancel this. Then 10 divided by 9.0. So this will give us 0.909% weight by volume sodium chloride. That is why they say normal saline is 0.909 sodium chloride. Is that okay? So that is how they actually got all these things. You can actually see here. Now let's see the next one.